So this is a question from the Ullman book, Database Systems, the complete book by Ullman, second edition. This is a question. This is exercise 3.2.7. So can we prove it? Basically, the question is saying if X is a set of attributes. Remember, of course, the question is here, what is X? X is a set of attribute. So what is X here? X is a set of attributes. Okay, some set of attributes. Okay, some set of attributes. So X is set of attributes, some set of attributes, or I can say basically X is subset of the database. Okay, in this X, you don't have all the attributes. It is not mandatory that you have all the attributes, but some set of attributes. Okay, it is some collection of attributes. This X is some collection of attributes. So is this statement true? Tell me, is this statement true? Closure of X, then if you do again, so basically closure of X plus is equal to closure of X. The statement is saying, what the statement is saying? The statement is saying that if you find closure of X plus, if you find closure of X plus, that will be X plus. If you find closure of X plus, that will be X plus. Is this statement true? Tell me, is this statement true? If you find closure of X plus, that will be X plus. Is this statement true? Yeah, this is statement true, right? This statement is true because you can notice what is X plus. Focus on what is X plus. Okay, what is X plus? X plus already contains every attribute that is determined by, okay, X plus already contains what? See, X plus will contain X, right? Agree? X plus will contain X, okay? Or I can say that X can determine. What X can determine? See, X plus will contain everything that X can determine. X plus will contain everything that X can determine, right? Okay, this is the definition. Agree? This is the definition. X plus will contain every attribute, okay, which can be determined by. So this is one attribute. X is set of attributes, but this is a single attribute. Okay, so you can notice this is a single attribute. This is a single attribute, and this is a, what is this X? What is this X? This X is some set of attribute. Yes or no? Some set of attributes. This can be single attribute also. This X can be single attribute also. Okay, some set of attributes. Now you can clearly see what is X plus. X plus is set of those attributes which X can determine. Yes, correct. Now you can notice very simple. You can notice that what X can determine. X can determine X. If X can determine X, that is trivial. Okay, that is a trivial. Okay, that is trivial. Trivially, X can determine X trivially. If X can determine, let's assume alpha. If X can determine alpha, okay, then this X plus. Now you will get those which are determined by X alpha. Yes or no? See, if X can determine alpha, then what I will say, then this X plus contains what? Then this X plus will contain what? Then this will contain those attributes which X alpha can determine. This is the recursive definition. Isn't it simple? See, this is a okay, this type of formal definitions they can give you in the exam. Formal definitions they can give you in the exam. This type of definitions they can give you in the exam because we already know. Let's take one example. Let's assume you have a relation A, B, C, D, E. Okay. And you have some set of functional dependencies, some random set of functional dependencies I'm giving you. Let's assume AB determines C. Okay. C determine D. Let's assume D, A determine E. Okay. Let's assume B, C determine A. Okay. Something like that. Okay. So I'm giving you something. Now you can notice. Now let's find out. Now here you can take that X is basically, for example, AD. Let's assume X is AD. Now we know what will be X plus. Initial definition of X plus says that X plus is basically anything that any set of attributes that X can determine, right? Correct? Right. Okay. So anything that X can determine, anything set of all the attributes that X can determine. Now you can notice. So this AD, what AD can determine? It can determine AD trivially. Okay. it can also determine what? Now you can notice this AD can also determine E. This AD can also determine E. Okay, this AD, if you notice, this AD can also determine E. Now, what this can determine, those things we will put. Yes or no? Now what we will put? Now you can notice, now in this X plus, now in this X plus, we will put those things which ADE can determine. Right? Okay. So now in this, we will put those things which ADE can determine. Correct? Okay. So here I can say, now in what AD plus closure will be? What AD closure will be? Okay. If I ask you what AD closure will be, now that will be all the things that ADE can determine. Tell me what ADE can determine. What ADE can determine. For example, let's assume that you also have this. Let's assume you also have this, that E can determine B. Let's assume you also have this. Okay, you also have this. So yes, we can say that. Yes, very good. So because remember, because AD can determine ADE, because AD can determine ADE, now I can say that AD closure will be equal to what? That will be ADE closure, right? Yes or no? Now I can say that what, okay, AD closure, like what AD can determine. So that will be same as ADE closure. Yes or no? Okay. So very simple, because whatever, so this is the definition. Now whatever ADE can determine, that also we will put. Okay, whatever ADE can determine, that also we will put. And this is the definition of what? Look at this and tell me what is this? This is the definition of what? This is the definition of what? This is the definition of ADE closure. This is the definition of ADE closure, right? Okay. This is the definition of ADE closure. So you can notice AD closure is equal to ADE closure. Now, what ADE can determine? What ADE can determine? You can notice ADE can determine B. ADE can determine B. Okay. So I can say ADE can determine ADEB. Okay. ADE can determine ADEB, right? Okay. Now again you can notice that ADE closure, what that will contain? That will contain everything. That will contain everything that ADEB can determine. That will contain everything that ADEB will determine. Okay, so I can say, okay, basically this closure will be same as this closure. So like this, you can keep going on. Yes or no? Like this, you can keep going on. So finally, I can say, for example, like what ADEB can determine. Okay, let's find what ADEB can determine. ADEB. So you can notice this AB, this AB, this can determine C. This AB, it can determine C. So I can say ADEB can determine C. Okay, and finally you can notice that, yeah, that's it. You got all the attributes. Okay, so like this. So can you notice? So some important results you can write here. Some important results you can write here. What are the important results you can write? These are the important results you can write. Okay, remember, these are the theoretical results they can ask you. Like you can ask that if X is any set of attribute. Okay, if X is any set of attribute or a single attribute, if X is any collection of attributes, okay, and X determines alpha, then what I can write? Tell me, then what I can write? Then I can write that X closure will be same as what? That will be same as X alpha closure, right? Yes or no? Is this clear? So X closure will be same as X alpha closure. So this is the simple point, a very simple point. So this is one note you can write. Okay. What another note we have seen? What another note we have seen? Another note that we have seen, let's assume if X is any set of attributes, if X is any set of attributes and Y determines alpha and Y is a subset of X, then what we can write? Then can we write this? Okay, then can we write this? X is any set of attributes. Can we write this? Can we write this? X is any set of attributes. Y determines alpha y is a subset of x, then can we say that x plus will be same as x alpha plus? Yes, this will be same, right? Because, okay, this is also true. Why this is also true? Because if, remember, y is subset of x, right? Y is subset of x. So if y can determine something, okay, and y is a subset of x, so x can determine y. So x can determine y because y is subset of x. So x can determine y. So you can notice that x can determine alpha. So x can determine alpha. So I can say that x can determine alpha. So x closure will be equal to x alpha closure. And the final result is what? The final result is that if you find x closure, that will be same as if you find x closure whole closure, because it will not give you anything new. See, in this you already have everything that x can determine. In this you have, or in this already, because why this result? See, because this result comes from where? This result comes from here, right? Yes or no? This result comes from here. This result comes from here. Because why? From where this result comes, think about it. This result, what is the proof? The proof is this. The proof is this. Can I say x can determine x plus? Can I say yes or no? This is the by the definition. Yes or no? This is by definition. By definition. Okay, x can determine x plus. Now you can think about this as alpha. You can think this as alpha. You can think this as alpha. So if x can determine alpha, then what I can write? Then what I can write? I can write x closure is equal to x alpha closure, right? Okay, yes or no? So you can notice x can determine x plus. So, okay, so here what I can say? Oh, okay, or in other direction also you can think. You can think in the other direction. Can I say x plus will determine x? Can I say x plus will determine x? This is trivial, right? This is a trivially. Yes or no? This will happen trivially. This will happen trivially. Okay, that x plus can determine x. So this will happen trivially. Now you can notice if something determines alpha, if anything, if z determines alpha, then what I can write? This result we know. If something, then I can say z closure is equal to z alpha closure. So similarly here I can say that x determines x closure. So what will be the closure of this? That will be equal to what? Okay. No, so this direction, in this direction we are not proving it. The other direction was correct. Okay, but the other direction was correct. Okay, okay. So the reverse direction was correct way of proving it. The reverse direction was actually the correct way of proving it, that if x can determine x closure, okay, this by definition of closure, by definition of closure. Okay, so, and you know this result. If you know this result, then you can notice x can determine x alpha, x plus. So this x plus will be equal to what? This x plus will be x plus whole closure, right? Yes or no? Because we know this. We know this. And there is no need to write x again. There is no need to write x again because the x is already included in x plus. So this is your proof. Is this clear? Anyone has any doubt in this? Tell me, is this clear? See, a simple, okay, you don't have to make it so like complicated. This is a simple result. And this result, Sagun, we already know this result. In the last class, we have already seen this result, right? This result we have already seen in the last class. If y is a subset of x, if y is subset of x and y can determine something, then can I say x can determine alpha? Then can I say x can determine alpha? Because y is subset of x. Because y is subset of x. Y is subset of x. Y is subset of x. So this will happen. Why this will happen? Sagun, can you tell me why this will happen? Can anyone tell me why this will happen? Why this will happen? Why this will happen? Because this is trivial depend. This is trivial FD. This is trivial FD. Yes or no? This is trivial FD. This is the trivial FD, right? Correct? Yes or no? Correct. So because y is subset of x, x is superset of y. So this is trivial FD, and y can determine alpha. This is given. Y can determine alpha. This is given. So we know so what will happen? So x can determine alpha. Okay. So this is the idea. So anyway, these some results are, these are some good results, like note number 1. Okay, note number 1, note number 2. Okay, these are some good results that you can write. And note number 3. Is this clear? Tell me, is this question clear to everyone? Prove that. So you can notice the closure of x closure will be equal to x closure. Have you seen this property anywhere? Have you seen this property? Have you seen this property in some other subject? In some other subject, have you seen this property? Like something plus is equal to x plus. Have you seen this property somewhere else? In the TOC, we have seen this, right? In the theory of computation. In the theory of computation, we have proven this. The proof we have seen, okay, the same property we have seen. In the theory of computation, the same property we have seen, that this property we have seen, that if R is regular expression, if R is a regular expression, okay, then R plus whole plus is equal to R plus. Okay, correct? Yes or no? This we have seen, this property we have already seen in the theory of computation. We have also seen that if L is any language, if L is any language, then L plus whole plus is equal to L plus. L plus whole plus is equal to L plus. These things we have seen. What is the difference between 1 and 2? What is the difference between first result and second result? What is the difference between first result and second result? Tell me, what is the difference between first result and second result? In the first result, you have regular expression. So it means the language is regular, right? Yes or no? In the first expression, in the first result, the R is regular expression. So your language is regular. But the second is talking about any language. This L can be any language, regular, non-regular, RE, not RE, okay? CFL, not CFL, RE, not RE, whatever language you take, recursive, not recursive. So whatever language you take, these things we have already seen, if you remember. Agree or not? This proof we have seen, this proof we have seen, these two proofs we have already seen. Okay. So in the theory of computation, this happens. In the theory of computation, this happens. And the same thing happens in the DBMS. In the DBMS also what happens? So I can say in the DBMS what happens. In the DBMS, you can say that if you have any set of attributes, then closure of this will be equal to X closure. Correct? So here X is any set of attribute. Here X is any set of attributes. Okay. And these small results you can remember. Okay. These small results. What are the small results? That if X can determine alpha, then if X can determine alpha, then X closure is the same as X alpha closure. Okay. So these small results you can remember. Okay. We have already seen this result. So if X can determine alpha, then X closure will be same as X alpha closure. Like whatever X alpha can determine, that we will put. Okay. So now let's move on. This is a very nice question. This is the, I can say, this is my favorite question from the Ullman book, Normalization Exercises. Did you try this question? Did you at least try this question? This question, this type of question come in the GATE exam. Yes or no? This type of questions, they come in the GATE exam. Have you seen the, like in the GATE exam, what they will do? They will define something new, right? They will define something new, some new definition they will give you. Okay. So they will say that, okay, consider this new terminology, a new terminology they will define. They will give you the definition. Then ultimately what you have to do in the GATE exam? if some definition is given to you, some new terminology is given to you, some new definition is given to you, okay, so then what you have to do? Then what you have to do? Tell me, what you have to do? You have to analyze, yes or no? Remember, at that point of time, your problem solving skills will matter, yes or no? Because in the GATE exam, if they give you some question from the notes as it is, from the notes, direct question comes, okay, then everyone will be able to solve. Everyone will solve that question, okay. You will not get any extra benefit because everyone will solve that question. But in the GATE exam, this type of questions where they give you some new definition, some new terminology, okay, some new terminology, and the definition of that terminology also they will give you, and then they will ask you some question. At that point of time, your problem solving skills will matter, your analytical skills will matter. And this is what we have done. This is what we have done from the day one, okay, from the day one of Go classes, from the day one, okay, from the first subject of Go classes. This is what we have done. Every day we are trying to improve your problem solving skills, we are trying to improve your analytical skills, yes or no? Every day, every single day, every single lecture, every single class, okay, we are improving, okay, our problem solving skills, we are improving our analytical skills, so that in the GATE exam any new question comes, okay, then you can handle it. Now let's solve this question. This is a very nice question. What this question is saying, read this question carefully and let's solve this question. The question is saying that, a very nice question. The question is saying that we say that a set of attributes is closed. We say that set of attributes, we say a new definition is given. A new definition is given to you. We say that a set of attributes is closed if x plus is equal to x. Okay, if x plus is equal to x. Now the question is saying a very good statement. Unknown set of FDs. FDs are not given. Set of functional dependencies are not given. But what the question is saying? But the question is claiming that if we are given which set of attributes are closed, then we can discover the FDs. Isn't it interesting? Like if I tell you which set of attributes are closed, if I tell you which set of attributes are closed, okay, then we can discover the FDs. So now three questions are given to you. In the three questions, okay, they are telling you which set of attributes are closed. Like in the third question, this set of attribute is closed, this set of attribute is closed. Okay, you don't have to worry about the empty set. You don't have to worry about the empty set because empty set cannot determine anything. Empty set can only determine empty set, right? Okay, empty set can only determine empty set. Empty set can never determine something else. It can never determine something else. Empty set can only determine empty set. So of course it is closed, right? Yes or no? So of course it is closed. See, okay, first you understand this question. Okay, let's understand this question. So our step one, what is our step one? Step one is understand the question, right? Correct or not? This is the understand the question. Understanding the question is the first step. Okay, so I'm giving you one relation. Let's assume I give you one relation ABC, and functional dependencies I'm giving you that AB can determine C, C can determine B. Okay, these are the functional dependencies I have given to you. Okay, now you tell me in this question which set of attributes are closed. In this question, remember this is a question I'm giving to you. Okay, and not X is closed. When can I say X is closed? What the definition is? When can I say X is closed? When can I say X is closed? The question is saying that we say that X is closed if X plus is equal to X. If closure of X is equal to X, right? This is what the question is saying. We say that X is closed. We say that X is closed if X plus is equal to X. The closure of X is equal to X. So if the closure of X is equal to X, now I am asking some questions. Which set of attributes are closed? Which is closed? Okay, some options I am giving you. Like for example, can I say A is closed? Can I say B is closed? Can I say C is closed? Can I say AB is closed? Can I say AC is closed? Can I say BC is closed? Can I say ABC is closed? Okay, so all the options I have given to you. And can I say empty set is closed? All the options I have given to you. All you have to do is check what is closure, yes or no. What you will do if you want to solve this question? If you want to solve this question, then what you will do? You will apply the definition, yes or no. If you want to solve this question, which is closed, then you will apply the definition, and what you will do? You will find the closure. What is the A closure? What is A closure? A closure is A, so that is closed, right? Because A closure is A, yes or no? Because A closure is A, so A is closed. Can I say? Because A closure is A can only determine A. What about B closure? Yeah, B can also determine only B. B can also determine B. C is not closed. This is C. This is not closed. This is not closed. Why? Because if you notice C closure, that will be CB. C closure will be CB. So C is not closed. What about AB? AB is not closed. AB is not closed because what is AB closure? Because what is AB closure? AB closure is ABC. Okay. Next, what about AC? AC is not closed. AC is not closed because what is AC closure? AC closure will be AC and C can determine B. AC and C can determine B. What about BC closure? Yes, this is closed because BC closure, if you find, that will be BC. ABC closure, can you notice set of all attributes will always be closed? Can you notice set of all attributes will trivially be closed, and empty set will always be closed. See, these are few results. What are those? Set of all attributes, set of all attributes, set of all attributes. This is trivially closed, right? Yes or no? Is it trivially closed? Is always closed? Is trivially, or I can say always closed? Always closed. Because if you take set of all attributes, then the closure will be set of all attributes, right? Because if you, for example, here if you find what is ABC closure, so ABC can determine ABC trivially. Okay, trivially. And you can notice the empty set is also closed, right? Because empty set can only determine empty set. Empty set can only determine empty set. Okay, only, yes or no? Empty set can only determine empty set. So I can say empty set closure, if you find, that will be empty set. So empty set is always closed, is always closed. So this information cannot help you, agree or not, that this is closed. Okay, this is always closed, and set of all attributes is always closed. Okay, so these two information, these are trivial. Now let's see this question. The question is saying all set of attributes are closed. Let's see the part 1. Can we find functional dependency? Can we find functional dependency? Can we find functional dependency if all set of attributes are closed? All set of attributes are closed. Okay, all set of attributes are closed. What the question is saying? What the question is saying? The question is saying that all set of attributes are closed, right? Yes or no? At all set of attributes are closed. Okay, now you find functional dependencies. Now you find functional dependencies. So you can notice that all the set of attributes are closed. So can I say that A plus, can I say that A cannot determine anything? Can I guarantee what A can determine? What can I say? Remember, all set of attributes are closed. All set of attributes are closed. Every set of attributes is closed. It means A plus is A, right? Because all set of attributes are closed. Every set of attribute is closed. Every set of attribute is closed. So I can say that, what I can say? I can say A plus will be A, right? By definition. Because every set of attribute is closed. The question is saying all sets of Ekta, the question, read the question. Set this and this are, is there any difference? Set of all attribute is closed and all set of attributes are closed. Read the question carefully. All sets of attributes are closed. All sets of attributes are closed. All sets that you can create, yes or no? The question is saying that all sets of attributes are closed. Read the question carefully. Okay, now let's see. So you can notice all sets of attributes are closed. Basically, it means that every set, whatever set you take, that will be closed. Is this clear? Whatever set you take, that will be closed. For example, if I take BC, for example, if I take BC, that will be closed. That will be closed. Whatever set of attribute you take, like if I take ADE, or maybe if I take, for example, ABD, if I take ABD, that also will be closed. So whatever set of attributes you take, that is closed. Is this clear? Is this clear, Ekta? Is this clear? So now you can notice, now from this question, what I can say? I can say that A plus will be what? A plus is closed. A is closed. So I can say A cannot determine anything, right? Similarly, B cannot determine anything because B cannot determine anything else. C cannot determine anything else. D cannot determine anything else. Can you notice? There is no non-trivial FD. Can you have non-trivial FD? In this situation, in this first question, can you have non-trivial FD? In the question number 1, can you have non-trivial FD? You cannot have non-trivial FD, right? You cannot have the, for example, you can notice you cannot have this FD. Why? This FD is not possible. Why? Why this is not possible? Why this is not possible? Because AB closure is equal to AB. Because AB closure must be equal to AB, right? Yes or no? Because AB closure must be equal to AB. So you can notice no non-trivial FD is possible. So in the question number 1, what will be the answer? In the question number 1, what will be the answer? No non-trivial FD possible, right? No non-trivial FD possible. There is no non-trivial FD. There is not a single non-trivial FD. There is no non-trivial FD. We do not have any non-trivial FD. So if they ask you some other question, they can ask you some other question. What they can ask you? They can ask you, if every set of attribute is closed, then what will be the relation? So this is another variation they can ask. This type of variation they can ask. What will be the normal form? Okay, this is the variation they can ask, that if every set of attribute is closed, if every set of attributes is closed, then what normal form? Then what is the normal form? Then the normal form will be, you can clearly see that in this situation, if every set of attributes is closed, then there is no non-trivial FD. Yes or no? In this situation, there is no non-trivial FD. There is no non-trivial FD. If there is no non-trivial FD, can BCNF violate? Can BCNF violate? Mavit, if there is no non-trivial FD, so BCNF cannot violate. Yes or no? So BCNF can never violate. If there is no non-trivial FD, so definitely you can notice what will be the normal form. That will be BCNF. You cannot violate the BCNF. Yes or no? To violate the BCNF, what do you need? Okay, if you want to violate the BCNF, like a relation is not in BCNF, if and only if what exists? A relation is not in BCNF. A relation R is not in BCNF. Is not in BCNF. If and only if there is some non-trivial FD. If there is some non-trivial FD where LHS is not super key. This is the definition. Yes or no? Is this clear? This is the definition. A relation is not in BCNF. A relation is not in BCNF if and only if there is some non-trivial FD. There is some non-trivial FD. There is some non-trivial FD. Some non-trivial FD where LHS is not a super key. Okay, so if there is no non-trivial FD, if you have no non-trivial FD, then definitely it will be BCNF. Okay, so this type of question they can ask. Let's see the second question. The only closed sets are these. The only closed set are these. The only closed sets are these. The only closed set. What this means? Let's see the second question. The only closed set. Your relation is RABCD. ABCD. This is your relation. And the only closed set, what are those? 5, ABCD. Yes or no? These are the closed set. And these are trivial, right? Basically, these are trivially, they are trivial ones. These are the trivial ones, right? These are the trivial ones. So which information is, no, we can infer something. Okay, we can infer something. Mavit, we can infer something. See, which information? See, they are not going to help you. These trivial ones will not give you any information. But who will give you the information? But who will give you the information? Who will give you the information? Yes or no? The things which are not closed, they will give you the information. Yes or no? Yes or no? Okay, the sets which are not closed will give you the information. Remember, the sets which are not closed, okay, which are not closed, will give us, in this question, will give us FDs. Will give us FDs. Correct or not? So remember, because the question is saying the only closed sets are these. These are the only closed sets. Okay. Now see, very good analysis. Very nice analysis is coming. Very nice analysis is coming. You tell me, if these are the only closed sets, then can I say that ABC will definitely determine D? Can I guarantee this? Can I guarantee this? Can you guarantee this? Why can you guarantee, Yuvraj? Why can you guarantee? What is the reason you can guarantee? This you can guarantee. Why? Because ABC is not closed, right? Because ABC is not closed. Because ABC is not closed, so it should give you something extra. It should give you something extra. Agree? If something is not closed, then it should give you something extra. And the only extra thing is this. Yes or no? So I can say this is not equal to this. So remember, one thing you can remember, one thing you can write, what not closed means. What not closed means. This you can understand. Okay, if X is not closed, what that means, this you can understand. If not closed, then what it means. If X is not closed, what it means? Tell me. If X is not closed, what it means? If X is not closed, then it should give you something extra. Yes or no? Then X should give you something extra. Then X should give you something extra, which is not part of X. Okay? Such that A does not belong to X, right? Agree or not? Do you agree? That X should give you something extra. Okay, if X is not closed. So if X is not closed, then it should give you something extra. So if X is not closed, then I can say that X closure is not same as X. So X closure will contain something extra. Okay, so I can say X closure will contain something extra. Right? So this point you can understand, and now you can solve the question. I can say that ABC will definitely determine D because ABC is not closed. So it will definitely determine D. Okay, now. See something interesting. ABC will definitely determine D. Okay, can I say ABD will definitely determine C? Can I say? Can I guarantee this? Can I guarantee this? Yes, I can guarantee because it is also not closed. ABD is not closed because you know ABD is not closed. So ABD closure is not same as ABD. Okay, because they are not closed. So I can say now something good is coming, something interesting is coming. Can I say AB will definitely determine C? Can I guarantee this? Can you 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 guarantee this? You can guarantee this. You can guarantee this. Why? Tell me. Do you guarantee that AB, because it is not closed, so AB will determine something new? Are you sure? See, okay, what I'm going to do, something interesting I'm going to do. What I'm going to do? This we want to check. Can you guarantee this? Can you guarantee this? Now see what happens. Look what happens now. Tell me, AB is not closed. So AB is not closed, right? So it should give you something extra. AB is not closed, right? AB is not closed. So AB should give you something extra. Tell me which extra thing. Tell me which extra thing. Tell me which extra thing. If it gives you C, then it will happen. If it gives you C, then this will happen, right? Let's try to stop it. Let's try to stop it. Okay, let me try to stop it. Is this clear? Are you getting my point? Let's try to stop it. Let's try to stop it. Okay, so to stop it, what I will assume that AB will determine D. AB will determine D. Okay, yes or no? If you try to stop it, then AB will determine D. Now, AB will determine D, and ABD will determine what? ABD will determine what? ABD will determine what? ABD will determine C. So can I say that AB is determining C, right? That's it. Is this clear? Tell me, is this clear? You cannot stop AB determining C. You cannot stop AB determining C. Is this clear? Yes or no? You cannot stop AB determining C. Isn't it like very nice question for the GATE exam? This is a question from the Ullman book. Ullman book is a standard book. Okay, Ullman is very popular person. In computer science, Ullman is one of the most popular person. Okay, Ullman. He has Turing Award. Okay, he won Turing Award. So Ullman is very popular person in computer science. In the field of computer science, Ullman is one of the greatest person. Okay, so you can notice this is a very nice question for the GATE exam. Is this clear to everyone so far? Tell me, is this clear? So I can guarantee that AB will determine C. AB will determine C. I can also say AB will determine D, right? Yes or no? So I can say AB will determine C. I can also say AB will determine D. You cannot stop it. You cannot stop. These things will happen. These things will happen. AB will determine. Okay, now, something interesting. Can I guarantee A will determine B? Can I guarantee A will determine B? Can I guarantee A will determine B? Take your copy pen. Can I guarantee A will determine B? Can I guarantee A will determine B? Okay, this is very simple. Can you guarantee A will determine B? This is very simple. See. A will determine something, right? Because A is not closed. Because A is not closed, it will give you something new. It will give you something new. Agree? Okay, agree or not? Because A is not closed, so it will give you something new. It will give you something new. Which new? Okay, give me something randomly. Give me something new. For example, let's assume it gives you C. Let's assume it gives you D. Okay, let's assume it gives you D. Now you can notice. So I can say that A can determine AD. Okay. Now you can notice AD. Is this closed? Is this closed? Is this closed? This is not closed. So it will give you something new. So it will give you something new, right? It is not closed. So it will give you something new. What new? Tell me something new. Okay. So you can notice whatever it gives you, like whatever it gives you, it is not closed, so it will give you something new. It is not closed, so it will give you something new. So it will give you something new. Isn't it interesting? Yes or no? So A determines B. So A determines B. You can guarantee that A will determine B. Tell me, what do you think if this question comes in the GATE exam? If this question comes in the GATE exam, what do you think? Pure analysis, pure analysis. Yes or no? Pure analysis. I hope this question becomes your favorite. This is a very nice question, like pure analysis, nothing else. So is this clear? So final, okay, let's come to the final conclusion. Let's come to the final conclusion. So in this situation, in the second question, what you can say? Your relation is ABCD and only closed sets are these. Only closed sets are these. What are the only closed sets? 5, ABCD. Only closed sets are these. So what is the conclusion? The conclusion is this, that A will determine B. Agree? Yes or no? That A will determine everything else. Okay, the conclusion is this, that you cannot stop it. Very simple. Very simple. You cannot stop it. You cannot stop it. You cannot stop it. You cannot stop it. If you try to stop it, you cannot stop it. So A can determine everything. Isn't it simple? A can determine everything. Okay, one more time I am going to tell you. One more time I am going to tell you. Let's try to stop. Okay, try to stop. Let's try to stop. What try to stop? Okay, tell me what we should try to stop. Tell me, just tell me something like, let's try to stop. Let's try to stop B determining D. Let's try to stop this. Is this clear? Okay, let's try to stop this. Try to stop. Don't let it come. Don't let it come. Don't let it come. Do not let it come. Okay, so try to stop this. Put your whole power. Okay, so now let's see. Tell me, is B closed? Is B closed? Is B closed? Is B closed? This is not closed, right? This is not closed. So if this is not closed, so what should I do? I should put something. It will bring something. Yes or no? It will bring something new. It will bring something new. Is this closed? Is this closed? This is also not closed. So it will bring something new. So it will bring something new. Is this closed? Is this closed? This is not closed. So it will bring something new. It will bring something new. That's it. That's it. That's it. Okay. So what you got? So can you stop it? Yes or no? Finally, you cannot stop it. Whatever you do, you cannot stop it. Yes or no? It is inevitable, you know? So I can say that it is inevitable, right? So I can say this is B determining D. You cannot stop it. It is inevitable. It is like Thanos. Okay. So it is inevitable. Run from it, dread it. Destiny arrives the same. Okay. Some small, okay. I will try better. But anyway, it is inevitable. Run from it. No. Okay. So good voice is not coming. Maybe you can try. Okay. Run from it, dread it. Destiny arrives the same. Okay. So anyway, so you can notice. So basically, I can say that you can, okay, everything can determine everything. So now you can notice B will determine A, C, D, C will determine A, B, D, and D will determine A, B, C. Okay. Is this clear? So finally, in the second question, what I can answer? In the second question, what you can say? In the second question, what are the candidate keys? A is a candidate key, B is a candidate key, C is a candidate key, D is a candidate key. Yes or no? This is a candidate key, this is a candidate key, this is a candidate key, this is a candidate key. What is your normal form? What you can guarantee? What is your normal form? What is your normal form? Every attribute is a candidate key. Every attribute is a candidate key. Every attribute is a candidate key. So it is BCNF. Every attribute is candidate key. Yes or no? If every attribute is candidate key, then can I say it is BCNF? Like two questions I am asking. Question 1. Every attribute prime. If every attribute is prime, then what you can guarantee? Then normal form that you can guarantee. Which normal form you can guarantee? If every attribute is prime. If every attribute is prime attribute, then what normal form you can guarantee? You can guarantee 3NF. Okay, but may or may not, this you can guarantee, but may or may not be BCNF. BCNF we cannot guarantee. Okay, but remember, if I give you that every attribute is a candidate key, if I give you every attribute is a candidate key, if I give you every attribute is a candidate key, then you can guarantee BCNF. Because you cannot create node super key. You can't even create node super key. Yes or no? You can't even create node super key, non super key. You can't even create node super key. Yes or no? Non super key does not exist. Non super key does not exist. You can't even create non super key. Okay, whatever you create, that will be super key. Non super key does not exist. Okay, if every attribute is super key, if every attribute is super key, then the same argument, then also same argument. So this was the second question. Now, can we try the third question? Can we try the third question? This third question. The closed sets are AB, comma, these are the closed sets. The question has given the closed sets. Okay, so now are you feeling this line? Are you feeling this line? Look at this line. If you know who are closed, if we are told which set of attributes are closed, we can discover the FDs. Isn't it very interesting? Like, okay, very interesting that if I tell you which set of attributes are closed, you can discover the FDs. Of course, you need a lot of analysis. Yes or no? You need analysis. Okay, let's see. So what this question is saying? AB, AB, CD. Let's see this question. Okay, so the closed sets are AB, AB, CD. The third question, can you take your copy pen? Take your copy pen. Question number 3. Okay, let's try this together. Let's try this together. So your relation is ABCD and the closed sets are given to you. The closed sets are given to you. Of course, this is always closed. This is always closed. These are trivial, but this is also closed. But this is also closed. A determining this is also closed. Okay, so the question has given you these closed sets. Yeah, these are the only closed sets. Okay, these are the only closed sets. Okay, now you tell me from this what you can say. This is another very interesting question. Analysis is coming. Yes or no? Analysis is coming. So if you are watching this video on the YouTube channel, on the GoClasses YouTube channel, if you are watching this video, okay, pause the video, try this question. Okay, don't watch like a movie. Pause the video, try the question, and then you can watch the video for the solution. Okay, and also press the like button and put a comment. Okay, this I request you everyone. Okay, I request everyone to put a comment. Okay, like, do you like these questions, all these sessions? Okay, so basically your feedback you can comment or comment something. Okay, comment something, because okay, so we need like we need more comments because our YouTube channel is not reaching to the more students. Okay, the quality, if you think we are providing the quality education, we are providing quality for the GATE computer science, then please help us reach more students. Okay, so comment and like. Okay, let's see this. So these are the closed sets, AB, ABCD, and phi. So what you can say here, see, this is another very interesting question. Now let's see this. First of all, is this closed? Is this ABD closed? Is ABD closed? You tell me. Is ABD closed? Is ABD closed? No, this is not closed. The question is saying the only closed sets are these. The question is saying only closed sets are these. So ABD is not closed. So can I say ABD will determine C? It will determine something new, right? So it will determine C. Okay, it will determine something new. What can you say about ABC? Will it determine D? Of course, because it is also not closed. So every three attribute will determine the another attribute, right? Do you agree that if you have three attributes, then it will determine the remaining? Do you agree? If you have three attributes, then they will determine the remaining. Okay, whatever three attributes you take, they will determine the remaining attribute. Okay, very simple. Now let's come. AB is closed. So can I say AB will determine something new? AB is closed. So no, it will not determine something new. Something interesting is coming. What about AC? What about AC? Will it determine something new? Okay, will it determine something new? Yes, it will determine something new because this is not closed. Okay. Can you prevent this? Can we prevent this? Can we stop this? Try to stop this. Try to stop this. Try to stop. Okay, try to stop this. Can you stop this? Can you stop this? This you cannot stop because AC is not closed. So it will give you something new. This is also not closed. So this will give you something new. So you cannot stop it. Inevitable. Inevitable. Yes or no? Agree? Agree or not? Inevitable. Because once you have three attributes, the fourth will definitely come. Remember, once you have the three, once you have any three attribute, remember, once you have any three attribute, the fourth will definitely come. Okay? Agar Karan aaya to Arjun bhi aayega. Okay, so if you have any three attributes, then fourth will definitely come. So you can notice here also, AC, you cannot stop this. Try to stop. If you try to stop, you cannot stop this because AC is not closed. So something new it will bring. Something new will come. Okay. So finally, I can say that it will always happen. So in this question, what can I say? Okay. So finally, what I can say here. So remember, if you have any three attribute, if you take any three attribute, the fourth will come. This we have seen. Okay. Also, what we have seen that any two combination like AC will bring some everything else, right? Yes or no? AC will bring BD. Is this clear? AC will bring BD. For example, you can notice CD will also bring everything, like every two attribute except for these two, except for AB. Any two attribute you take except for AB, okay, that will bring everything else. Yes or no? Correct? For example, AD will bring everything else. Is this clear? For example, BC will bring everything else. Are you getting this point? For example, BD will bring everything else. BD will bring everything else. So basically, any two attributes you take other than these, they will bring everything else. So this is the another point. Any two, okay? Any two you take except AB. Any two you take except AB. Except AB. Except AB. So any two you take except this combination, the remaining two will come. Okay, isn't it very like interesting? Yes or no? So very simple. So this is the analysis that we have done so far. Now something interesting will come now. Okay, Something interesting will come now. What is that? Okay, what do you think? What is C plus? What do you think? Is this closed? Is this closed? Is this closed? Is this closed? Okay, look at C. What C can determine? What C can determine? Tell me what C can determine. See, notice. Can you stop this? Can you stop this? Can you stop this? You cannot stop this. Why? Let's try to stop this. Let's try to stop this. Let's try to stop this. Remember, C is not closed. C is not closed, right? So because C is not closed, so C will bring something new. Let's try to stop C determining A. We are trying to stop C determining A. So it will bring something new. It is also not closed. Okay. Here you can stop. Because you know two attributes other than AB. Two attributes other than AB. Two attributes other than AB. Yes or no? You have two attributes. You have two attributes other than AB. So it will bring everything. Okay. So you can notice it will bring everything. So that's it. Can you stop this? So you cannot stop this. So finally, what I can say, can you notice that C will bring everything? You cannot stop anything. C will bring everything. C will bring everything. C will bring R. Similarly, D will bring R. Similarly, D will also bring R. You can check it out. Okay. The same way, D will also bring R. Okay. Now, what A will bring? What A will bring? What A can bring? What A can bring? Can A bring C? Can A bring C? A simple question I am asking. Can A bring C? If A brings C, there will be a problem. If A brings C, there will be a problem. There will be a problem. What is the problem? If A brings C, then AB is not closed. Then AB will bring ABC. So then you can notice this is not closed. Problem? Because remember, AB should bring only AB. Yes or no? AB should only bring AB. This is the problem. Because AB should only bring AB. AB should only bring AB. This is the problem. AB should only bring AB. So if A brings C, then there will be problem. So A cannot bring C. Clear? Okay, clear or not? Interesting analysis is going on. The complete use of the brain is going on. Yes or no? The complete use of the brain is going on. Okay. Is it possible that A does not bring B? Is it possible that A does not bring B? See, you can, okay. So what I can say here? So what we got? That A cannot bring C, right? So this is what we got. So A cannot bring C. Similarly, A cannot bring D, right? So A cannot bring C, and similarly A cannot bring D, right? Is it possible that A does not bring B? Is it possible that A does not determine B? Is it possible that A does not determine B? Is it possible? If A does not determine B, then what will happen? If A does not determine B, then what will happen? Then A will be closed. Yes or no? Then A will be closed. Because A cannot bring C, A cannot bring C, A cannot bring D. If A cannot bring B, then A will be closed, which is a contradiction, which is a problem. Which is a problem, because the question is saying that this is not closed. So this is a problem. So A should determine B. So finally I can say, is it possible that A does not determine B? This is not possible. So finally what I can say, this is the final conclusion. Let me give you the final answer. So this is the final answer, that A will determine B, B will determine A. Okay, A will determine B, B will determine A, and C will determine everything. C will determine everything. and D will determine everything. This is your final answer. This is your final answer. What are the candidate keys? What are the candidate keys? C is a candidate key. D is a candidate key. C is a candidate key. D is a candidate key. That's it. These are the candidate keys. The relation. What can you say about the normal form? What can you say about the normal form? Definitely in 2NF, right? Because every candidate key is simple attribute. Every candidate key is a simple key. Every candidate key is a simple key. So subset of candidate key is not possible, right? Proper subset of candidate key is not possible. So violation of 2NF is not possible. What about 3NF? What about 3NF? What about 3NF? What can you say about 3NF? This is the violation of 3NF, right? Yes or no? So you can notice this is in 2NF, not in 3NF. 2NF, not in 3NF. Not in 3NF. Okay, because this is the violation of 3NF. Why this is violation of 3NF? Because A is non-prime and B is not super key. Yes or no? See, B determining A. Here this is non-prime. Here this is non-prime. And this is not a super key. And this is not a super key. So this is violation of 3NF. So this whole thing, this is the violation of 3NF. Okay. So this was your question. This was the Ullman question. I hope you got it. The complete analysis we have done. But this is not the end. But this is not the end. Yes or no? In the GATE exam, if this question comes, in the GATE exam, if this question comes, then they will not ask you these three. Yes or no? They will not ask you these three. They will not ask you. They will give you something. For example, they can give you that A is closed, ACD is closed. Something they will give you. Yes or no? In the GATE exam, if this question comes, they will give you something else. These three they will not give you because these three we have done. Okay, these three we have done. So they will give you fourth. Now, after these three, can you guarantee that I will be able to solve fourth, fifth, sixth, 10th? Tell me. After these three, can you guarantee, are you confident that you will be able to solve any variation? You will be able to solve any variation. Are you confident? Yes or no? Okay. So at this point of time, you can pause the video. If you are watching on the YouTube channel, pause the video and put your comment. Okay. Put your comment, like the session, like the video, and put your comment and share with all the GATE aspirants. Okay. So now, anyway, let's move on. Nikhil, is there any doubt? Nikhil, is there any doubt? You try this. This is not complicated. Ekta, Nikhil, just try this. Okay. If you are watching this like a movie, then maybe it will become difficult. But if you take your copy pen, if you take this pen in the hand and if you do something, then it will become very easy. This is your question from the Ullman. A very nice question. Okay, let's move on now. This single question can improve your analytical skill a lot. Yes or no? This single question can improve your knowledge of closure of attributes, closure of attributes, functional dependencies, properties of functional dependencies. So this single question can basically, I can say, it will improve your analytical skills. This single question will improve your problem solving skills. So this type of questions are very good. Okay, let's move on. Let's see this question. This is another question from the Ullman, from the database systems, the complete book by Ullman. Okay, so tell me the answer for this question. This is another very simple question. Consider a relation RABC such that each attribute functionally determines the other two attributes. Okay, each attribute functionally determines other two attributes. Find all the minimal cover for FDs. Find all the minimal covers. Minimal basis means minimal cover. Okay. So this is another very easy question. Before you see this question, some misconceptions and some note I want to tell you. Minimal cover. What is the another name for this? Minimal cover. Like the another name you can see, that is minimal base. Minimal bases. Yes or no? The another name you can notice is minimal bases. The another name is canonical cover. And what is the another name that is the actual word? Yes, the actual. Remember. These things can confuse you because minimal does not mean here minimum number of FDs. Yes or no? Here minimal cover does not mean minimum number of FDs. Minimal cover does not mean minimum number of FDs. So the fourth word is actually the correct word. The fourth word is actually the correct word. What is the fourth word? That is irreducible cover, or I can say irreducible set. Irreducible set of FD. Yes or no? This is the, so in the GATE exam, they can ask you, minimal cover, they can ask you canonical cover, they can ask you minimal base, they can ask you irreducible set of FDs. All these things are same. All these things are exactly same. Remember, irreducible set of FDs, which you cannot reduce. Okay. So when I say irreducible, what I'm talking about? When I say irreducible, then what you cannot reduce? Irreducible set of FDs. What it means? Tell me what it means. It means no extraneous attribute on the LHS. Agree? No extraneous attribute on the LHS. No extraneous attribute on LHS. And no redundant FD. No redundant FD. Okay, yes or no? So these are the two things you have to do. Okay, anyway, the question is saying that every attribute determines the remaining two attributes. The question is very simple. What the question is saying, in the question R, A, B, C is given, and the question is saying that A can determine BC, B can determine AC, and C can determine AB. You start from here. You tell me, this is your FD that is given to you. Okay, this is the given set of FDs. This is the given set of FDs. My first question, is this minimal? Is this minimal? Is this irreducible? Is this irreducible? First of all, on the LHS, you don't have to check anything. Agree? Do you agree with me? On the LHS, you don't have to check anything because on the LHS, only single attribute is there. So you don't have to check this. You don't have to check extra attribute on the LHS because on the LHS, single attribute is there. On the LHS, single attribute is there. So on the LHS, you cannot have extra attribute, extraneous attribute. But you can notice, some FD is redundant. How to know some FD is redundant? How to know? Okay, how to find redundant FD? Remember one thing I want to tell you, one very clearly I want to tell you, see, how to find redundant FD. Finding redundant FD. How to find that? Finding redundant FD. So first of all, what is your first step? Always on the RHS, you have a single attribute. Okay, this is, I can say, this is your step one. Why this is step one? This is only for convenience. This step one is only for convenience. See, this is only for convenience. The step one is only for convenience so that you don't make mistake. This is only for convenience so that you don't make mistake. So this step one is only for convenience. For convenience on RHS, keep single attribute. Keep single attribute. Can we always do this? Can we always do this? On the RHS, can we have single attribute? Can we always do this? Yes, we can always do this, right? We can always do this because you already know that if you have alpha determining AB, then you can write it. You can write it. What you can write it? If you have alpha determining AB, if you have alpha determining AB, you can write it alpha determining A, you can write it alpha determining B. So like this you can write. Okay, anyway, now what is the step 2? Step 2 is very simple, that this is your set of FDs. This is your set of FDs. If you want to check, is this FD, if you want to check if this FD is, okay, look at this FD, X determining Y. If you want to check, is this redundant or not? To check if this is redundant or not, what you will do? To check if this is redundant or not, then what you will do? In the remaining you will find X closure. Yes or no? In the remaining you will find X closure. In the remaining you will find X closure, right? Agree? So in the remaining you will find X closure. If X closure contains Y, then what you will say? In the remaining, okay, in the remaining you will find X closure. If X closure contains Y, then what I can say? Then I can say this X determining Y was redundant. Is redundant. Yes or no? So this X determining Y, this is a redundant. Okay, very simple. This is the method. Okay, so I can say now here, tell me, A determining B, A determining, I cannot remove the complete thing. Yes or no? A determining BC, I cannot remove. Agree? Just think about it. Let's assume I remove it. Okay, from the remaining, what is A closure? 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 That is A. So I cannot remove it, right? Yes or no? Do you agree I cannot remove it? Do you agree? I cannot remove it. Okay, but can I remove this? Can I remove A determining B? Now, in the remaining, you find A closure. In the remaining, you find A closure. What is A closure? That will contain B. So I can remove B, right? So is this reducible? Irreducible? The answer is no. Is this irreducible? The answer is no. Why? Because you can clearly see that A determining B, this is redundant. This is a redundant. Okay, now let's move on. Now the question is asking all the minimal covers. Now let me find out. So you know that this is a redundant, right? So first of all, before we solve this question, let me write this in this manner, that A determining B. Okay, let me write it in this manner. A determining B, A determining C, B determining A, B determining C, C determining A, C determining B. Okay, so this is your FDs. Now let's find out the minimal covers. Okay, you tell me one by one. Is this redundant? Is this redundant? Is this redundant? Yes, this is redundant because the remaining, this is redundant, right? Why this is redundant? What is the reason this is redundant? This is redundant because the remaining people can bring C. The remaining people can bring B. Okay, in the remaining, if you find A closure, then that will be ACB. So, okay, the remaining people can, in the remaining people, A closure contains B. So you can remove this. Okay, now this is gone, remember. Now this is gone. So now forget about it. Now this is gone. Okay, remember this is gone now. Now this is gone. So now forget about it. Can I remove this A determining C? Can I remove this A determining C? Can I remove this? You cannot remove this. You have to keep it. You have to keep it. Okay, what about what about this B determining A? Can I remove this? Let's assume I remove this. Okay, and this is already gone. Remember, this is already gone. Remember, this is already gone. Remember, this is already gone. Okay. Is this clear? So remember, this is already gone. Okay, you tell me. So this is mandatory. You tell me, if I remove this, What is B closer? If I remove this, what is B closer now? If I remove this, what is B closer? So B closer, you can notice, can B bring A? If I remove this, can B bring A? Yes, B can bring A transitively. Here you can notice B can bring A transitively. So I can remove this. So this is also gone. So this is also redundant. I can remove this. So this is also redundant, right? Okay, so this is also gone. Now forget about this. This is also gone. You have removed this. Okay, what about the remaining? B determining C. Okay, what about this? Can I remove this? Now you cannot remove this, right? You cannot remove this. What about C determining A? Can I remove this C determining A? Can I remove C determining A? Now can C determine A? No, I cannot remove this. I cannot remove this. Okay, can I remove C determining B? Can I remove C determining B? Can I remove C determining B? I cannot remove. Okay, so did you notice? This is your minimal cover. So in the minimal cover, how many FD are there? So this is a possible. So finally you got a minimal cover. Finally you got a minimal cover. What minimal cover you got? What minimal cover you got? A determining C, B determining C, C determining A. And remember, this is minimal cover. Remember, this is minimal cover. Remember, this is irreducible set. You cannot reduce further. This minimal does not mean minimum number of FDs. Okay, you cannot reduce further. This is irreducible. Irreducible. You cannot reduce further. Okay, is this clear? Now, one very important point I want to tell you. What is that? Very, very, very important point I want to tell you. Can you notice that actually for this, what I can do this. Okay, actually now notice. The order matters. The order of elimination, the order of removal. Okay, remember, the order of removal of redundant items matters. The order of removal of redundant items, that matters. Redundant items matters. In which order? In which order are you removing the redundant items? Okay, in which order you are removing the order, that matters. The order matters. Is this clear? This order will matter. In which order are you removing? The order will matter. Now. See. Okay, tell me. Is this redundant? Just see this and tell me, is this redundant? A determining C. If I remove, can A determine C? If I remove, can A determine C? Yes, A can determine B, B can determine C, so I can remove this. Do you agree that I can remove this? Okay, so I can remove this. So this is gone. Okay, so this is gone. This is gone. So I can remove this. This is redundant. Now forget about this. Now you tell me. Okay, can I remove this? Can I remove this? Look at this and tell me. Can I remove this? If I remove this, okay, and this is also already gone. Can B determine A? Yes. B can determine C, C can determine A. So B can determine A, right? So this is also gone. Okay. No, notice. What I will do. Can I remove this? Can I remove this? Can I remove this? If I remove this, can C determine B? Yes. C can determine A can determine B. Array, C can determine A can determine B. So I can remove this also. So this is also gone. This is also gone. So what minimal cover I got? So what minimal cover I got? I got A determine B, B determine C, C determine A. Did you notice here you have 3 FDs? This is also minimal cover. This is also minimal cover. This is also irreducible. You cannot reduce it further. But did you see the difference that this is also minimal cover, this is also minimal cover, and this is also minimal cover. Here you have 3 FDs and here you have 4 FDs. You have 4 FDs here. Tell me one question I want to ask. Here you have 4 FDs and here you have 3 FDs. So can I say this is minimal cover and this is not minimal cover? Can I say? Can I say this is not minimal cover? Can I say this is not minimal cover? No, you cannot say that. Because remember, this I told you. The screenshot also I gave you. What was the screenshot? From the Navate. Do you remember? From the Navate, I gave you the screenshot. So this is a misconception. First of all, okay, minimal cover, it simply means. What minimal cover means? So whenever you say minimal cover, it simply means irreducible set of FD. It simply means irreducible set of FD. Okay. It has nothing to do with number of functional dependency. Yes or no? It has nothing to do with set of functional dependencies. Number of functional dependencies. So this minimal cover has nothing to do with number of FDs. Yes or no? Number of FDs. Is this clear? So the number of FDs does not matter. The only thing matters is this. This is the only thing that matters. Irreducible set of FDs. This has nothing to do with number of FDs. Is this clear? Tell me. This has nothing to do with number of FDs. So this type of question you will find in the test series. In some test series, in some Hulu test series, you will find this question. You will definitely find this question. You can check it out. Okay. Some Hulu test series will give you this question that this is the set of functional dependency. Number of FD in the minimal cover. Number of FD in the minimal cover. This is what they will ask you. Okay. They will ask you the number of FD in the minimal cover. At that point of time, what you can do, what you will do at that point of time, when you see this question that a set of functional dependency is given to you and they will ask you number of FD in the minimal cover, what you will do? Skip that test. Skip that test series. Okay. Skip that test series. So is this clear to everyone? So remember, minimal cover has nothing to do with number of FDs. Is this clear, everyone? See, this question is possible. Sagun is asking, how many minimal cover are there? Any shortcut for this? There is no shortcut for this. This is an NP hard problem. This is an NP hard problem. So in the GATE exam, they will not ask you this. In the GATE exam, they will not ask you this. Let me tell you. In the GATE exam, they will not ask you how many minimal covers are there. Number of possible minimal covers. They will not ask you. This is an NP hard problem. Okay. So they will not ask you. If by chance they ask you, they will give you a very small relation. If by chance question comes, it will not come. See, it will not come. They will not ask you number of FD in the minimal cover. They will not ask you number of minimal covers. These two questions they will not ask you. The first question they will not ask you because that is nonsense. Number of FD in the minimal cover, that is nonsense. Because different minimal covers can have different number of FDs. Yes or no? Minimal cover has nothing to do with number of FDs. Different minimal cover, they can have different number of FDs. But remember, they cannot ask you, they will not ask you number of minimal cover because that is very complicated. Yes or no? That is NP hard problem. So they will not ask you that. So you don't have to worry about this. You only have to worry about that. Do you understand what is minimal cover? Yes or no? You only have to think about, do you understand minimal cover? All your misconceptions of the minimal cover are gone. Okay, this is what is important. So remember, order matters. Okay, is this clear? So like this, and can I give this as a homework? More minimal cover can you find? Can I give this question as a homework? Tell me. Like 2 minimal cover I have found. Can you find more minimal covers? There are more. I guarantee you there are more. I think there are 2-3 more. I think 2 or 3 more minimal covers are there. You don't have to find the exact cover. See, in the comments you write your minimal cover, which I did not give. I have given 2 minimal cover. You give me third minimal cover. Okay, you give me third minimal cover. It is possible there can be 4 or 5 minimal covers. 2 I have given to you. It is possible there are 5, maybe 4, 5 or 6. Okay, I don't know. Okay, but definitely there are more. At least 1 or 2 more minimal cover you can find. At least 1 or 2. So in the comment you write your minimal cover. Okay, and how will you do that? Just change the order. Yes or no? Just change the order. Agree? This order you change. Order of elimination, order of removal of redundant items that you change, you will get new minimal cover. Is this clear? Okay, so this I give you as a homework. 2 minimal cover I have given to you. The remaining minimal cover you find and you write your answer in the comment. Okay, 1 extra minimal cover if you can give, that is fine. That is enough. Just do some random order. There are 6 items. Yes or no? Can you notice there are 6 items? There are 6 items. These are the 6 items. Okay, remove them in some random order. Okay, for example, first you can remove this, or maybe first you can remove this. Okay, then you can remove something else. So you can start from here. You can remove this, then you can remove something else. So okay, so like this. So find more minimal covers. This is your homework. Find more minimal covers. Okay, so this is your homework and write your answer in the comment. Okay, so let's move on. Let's see this. Mavit is saying, Mavit is asking, is this minimal cover concept, is this related to maximal or minimal matching? No, not like that. Mavit, I don't think there is any connection. Okay, but like which type of connection we are looking for? Yes or no? Okay, so okay. So anyway, I think there is no connection. I think there is no connection. Okay, but the question is, if we are looking for some connection, then what type of connection we are looking for? Okay, what type of connection? Because in every subject, this type of concepts will keep coming. Okay, this type of concept. But remember one thing, Mavit, we have a concept of minimum matching. We have concept of matching number. Yes or no? Sorry, we have a concept of matching number. What is that? Concept of matching number. What is matching number? That is the largest possible matching. Yes or no? We have a concept of minimal matching number. Matching number means what is your maximum size matching you can create. What is the maximum size matching you can create? Similarly, there is a concept of vertex covering number. Okay, so there are these concepts, but here in the canonical cover we don't have this concept. Is this clear? In the minimal cover we don't have this concept. We don't have this concept. Okay, now let's see this. Okay, so tell me here, this is your question. It is sufficient to give a minimal base for the full set of FDs. This is a very nice question for practice. A very nice question for practice. What the question is saying? The question is saying that R, A, B, C, D, E with some set of FDs, we wish to project those FDs. Oh, this is a nice question. See this. What this question is saying. Look at this. What this question is saying, one of them I will do, the remaining I will give you as a homework. But what this question is saying, that these FDs are given on the relation. Is this clear? These FDs are given on this relation. On this relation R, these FDs are given. And the question is saying we wish to project these FDs on the relation S, ABC. Give the FDs that hold on ABS. This we have done this, right? In the dependency preserving. In the dependency preserving, we have done this. Okay, so what is this concept? I told you what was the concept. The concept is very simple. You have a relation, you have a universal relation, right? You have a universal relation, like you have a universal relation R. Okay, for example, A, B, C, D, E. This universal relation R has some FDs. It has a FD set. In this FD set, you have many FDs, right? Okay. Now what you do? Now you create a sub relation. Now from this you create a sub relation. You create a sub relation. Okay, and that sub relation is, for example, maybe you are creating ACE. Then you want to find the FDs that hold on this relation, right? Yes or no? What you do? You find projected FDs. You find projected FDs on S. Or I can say find FDs that hold on S. FDs that hold on S. That hold on S. So this we have done, if you remember. Find all the FDs that hold on S. That hold on S. That hold on attributes of S. Okay, that hold on S. Those FDs we have to find. Now let me take the first question. I will only do the first question. The remaining questions you can do. Okay, let me do the first question. The first question is saying SABC. So there is a step-by-step procedure to do this. Remember, there is a step-by-step procedure to do this. If you have a relation, if you have a universal relation, okay, and you want to find, there is a step-by-step procedure. So let me do this. The option 1, that is AB determining DE. AB is determining DE and C determining E. C determining E. D determining C. D is determining C. And you can notice E determine A. There is a step-by-step procedure. If you, these are the FDs, these are the overall FDs in the R. These are all the FDs that are there in the database. Yes or no? We want projected FDs. What do we want? We want projected FDs. We want projected FDs on S, which is ABC. On ABC, what are the projected FDs? This is what we want. There is a step-by-step procedure to do this. There is, okay, you don't have to do this randomly. There is a step-by-step procedure. What is that? There is a step-by-step procedure. You don't have to do randomly. There is a step-by-step procedure. Just find what is a closure. Yes or no? In this, what you find a closure. Just find a closure. In this, what you find a closure. What that will be? In this, you find a closure. What that will be? Tell me. In this, if you find a closure, that will be A. In this, you find B closure. In this, you find B closure. Your focus must be on ABC. Your focus you keep on ABC. So what is B closure? That is also B. What is C closure? C closure is CEA. What is C closure? In this, what is C closure? That is CEA. And okay, so CEA. That's it. Yes or no? CEA. So now this you can project in the ABC. Yes or no? This you can project on the S. In the S you can write this. In the S, what you can write? You can write C determining A. This is what you can write. This is your first. Isn't it simple? Like step-by-step procedure is there. You will not make any mistake if you will not make any mistake if you go step by step. And if you go randomly, definitely some FD you will miss. If you go randomly, definitely some FD you will miss. There is a step-by-step procedure. You can do that. You will not make any mistake. Okay. Find, your focus must be on what? Only on ABC. See, I am not finding E closure. Did you notice? I am not finding E closure. I am not finding E closure because I only want to focus on ABC. Okay. What else I need to find? What is AB closure? Okay. What is AB closure? AB closure. What is that? AB closure is ABDE. AB closure is ABD and D can determine C. So that is ABCDE. Okay. So from here, what I can say? So from here, what I can take? From here, I can take what? So from here, I can take this. So from here, I can take that. AB can determine C. Okay. What else? Now, similarly, you step by step, you find what is BC closure you find, and then AC closure you find. So you find BC plus, in this you find BC closure. The BC closure will be BC. Okay, the BC closure will be BCE, BCEA. Okay, the BC closure will be BCEA D, right? So you can also write that BC will determine A. BC will determine A, right? Correct? BC will determine A, right? So your focus must be only on BC, must be determine A. So BC determining A. What about AC plus? What about AC plus? AC plus, it will determine ACE. Okay, AC plus, if you notice, so that will be ACE, ACE. That's it. So only this is your FDs. Yes or no? You don't have to find ABC plus. Agree? You don't have to find ABC plus. You don't have to find ABC closure because that will be ABC. Okay, so that is trivial. So you don't have to find that. This is your question. This is done. Okay, let me also see option number C. Okay, let's also solve like 2 questions. I will solve, the remaining 2 you can try. Okay, let me solve the option C also. What is option C? AB determining D. Did you try this? AB determining D. AC determining E. AC determining E. BC determining D. BC determining D. D determining A, E determining B. D determining A, E determining B. Okay, so like this. Okay, now let's see this. So again, step-by-step procedure is there. Remember, there is a step-by-step procedure. We will keep our focus on ABC. We will keep our focus on ABC. We will find A plus. What is A plus? A plus is nothing. So, okay, so there is nothing to check because A plus is only A. We will find B plus. What is B plus? That is B. So there is nothing here also. We will find C plus. What is C plus? That is also C. So there is nothing here. They will not give you anything, right? Agree? They will not give you anything. Now you take two items at a time. Okay, what is AB plus? AB plus will give you AB. Okay, AB plus, that will give you AB. AB will give you D. And now you can notice that D will give you A. So AB will give you D and D will give you A. That's it. So, okay, here also nothing. Here also nothing. What about AC plus? What about AC plus? AC plus will give you AC. That will give you A. That will give you E. E will give you B. AB will give you D. Okay, so A, B, C, D, E. So you got everything. So here, your focus must be on what? Your focus must be, actually you can stop here. Can you notice? You can stop here. As soon as you get B, you can stop here. Agree? You can stop here. As soon as you get B, you can stop here. Okay, next, what about BD? What about BD plus? BD plus will be, that will be BD. D can determine A. Okay, so you can notice BDA. That's it. Okay, so this also will not give you anything. Sorry, BC. Okay, we have to check BC. BC plus we have to check. We have to check BC plus. So the BC plus will be BC, and BC can give you D, D can give you A, and this A, then you can notice. Okay, so then you can notice AC can give you E. Okay, so here I can say that BC determining A. So here you can stop. Here you can stop. AC determining A. So at that point of time, you can stop. So this will be your answer. Is this clear? This is your answer. Yes or no? Very simple. So this is the simple answer. Very simple. Okay, the same question actually, if I ask you as ADE, if I ask you as ADE, now what will be the answer? If I ask you as ADE, in the same question, if I ask you as ADE, now what will be the answer? Now your focus will be on ADE, correct? Now your complete focus will be on ADE. Actually, you can do this question in a step-by-step manner, but without taking copy pen. Without taking copy pen, you can do. Very quickly, you can do. Very quickly, you can do. So you can notice A plus will be A. And what is D plus? D plus will be DA. D plus will be DA. That's it. So you can say that D can determine A. Here you can write. Yes or no? You can say D can determine A. Next, you can find E plus, that will be EB. That will be EB. Okay, so that will be EB, nothing else. So you are getting nothing from here. Then you can check AD plus. AD plus will be, AD plus will give you nothing. AD plus will give you nothing, but you can check. Okay, anyway. So it will give you nothing. It will give you only AD. After that, you can check AE plus. What is AE plus? That will give you AE. Okay, and E will give you B. And this AB will give you D. And you can notice this. Can someone give you C? No one can. Can you notice no one can give you C? Okay, anyway, but we don't care about C, right? We don't care about C. We only care about that AE determining D. We only care about this. We don't care about C. Okay, what about the remaining? For example, we can also check that what is ED plus. ED plus will be ED. Okay, so that will be EDA. So that's here you can stop. Here you can stop. Here you can stop. Here you can stop. ED determines A. This is your answer. Okay, here you can stop. Okay, here you can stop. ED plus will be actually EDA. Okay, and you can notice B will also come. Okay, so these things will come. But anyway, you can stop. What you can say? You can say that ED will determine A. So that's it. This is your answer. So this is how you can do these questions. Is this clear? Tell me. So all these questions you can do. Basically, Nikhil, the question is just saying that whatever you give, okay, you can give any set of FD. Okay, you can give any set of FD. For example, like here, is this minimal? Is this minimal? This set of FD, is this minimal? Is it minimal? Look at this and tell me, is this minimal? Can I say this is minimal? Can I say this is irreducible? Can I say it is irreducible? Tell me. Can I say it is irreducible? So first you check the extraneous attribute. Remember, first you check the extraneous attribute. Is this minimal? Is this irreducible? Okay. So for that, what you need to do? First you check the extraneous attribute. Remember, C determining A, AB determines C, BC determines A. Okay, C determines A. So first of all, you check extraneous attributes. Okay, first of all, this is what you do. What is the extraneous attribute? When can you say that? This is a simple point. That when can you say that? If you have this type of situation, let's assume this is your FD set. This is your FD set. Okay, and in this FD set, if you have XA determining something, XA determining something, then when can I say A is extraneous? A is extraneous. A is extraneous in this. A is extraneous in this. When can I say in this? A is extraneous. If A is extraneous in this, if X can determine, if X plus, you find X plus. If X plus contains B. If X plus contains B. Okay, here don't remove A. Okay, will you check by removing A? Will you check by removing A? Will you check by removing A? Tell me, will you check by removing A? No, you will not check by removing A. No. Okay, so remember, A is extraneous. This A will be extraneous if X can determine B. If X plus contains B. Without removing A. Check without removing A. Okay, find X plus without removing A. This is important. Okay, because many students, what they do, they remove this A. Okay, this is a common mistake that they remove this A. They remove this A. Okay, so find X plus without removing A. So don't remove this A, just find X plus. If it contains B, then you can remove. If you find that this is extraneous, then you can remove. Is this clear? Like if I find that this is extraneous, if I'm sure this is extra, then I can remove. Is this clear? Okay, so here also you can notice that. Tell me, in this you notice, let's see this. Is this A extra? Is this A extra? Tell me. In this question, is this A extra? In this, can I say A is extra? Like, just find out B plus. Okay, in this A is extra. This is my question. Your question is A in this. Is A extra in this? Is A extra in this? So what you will do? If you want to be sure, then what you will do? Your answer will be what? You will find B plus, right? So your B plus is only B. So okay, so I can say so not extra. So A is not extra, right? Agree? So A is not extra, because you will find B plus and that is only B. So A is not extra. What about B? Is B extra? The second question, is B extra? Is B extra? In this AB determining C, is B extra? Is B extraneous? So the answer again, in this again, what you will find? You will find A plus. A plus is A. So B not extra. B is also not extra. Okay. Here B is also not extraneous. So remember, like this you can do. Actually, can you notice? I am writing, but you don't have to write this. Yes or no? You can do this verbally. You can do this verbally. You don't have to write this. I am writing this so that you can understand, but you don't have to write this. For example, look at this, focus on this. For example, focus on this. In this, can I say B is extra? Can I say B is extra? This B is extra, right? Because C, in this, if you notice, in the complete, if you notice B, if you notice C plus, so C plus contains A. C plus contains A, correct? Okay, so C plus, that will contain A. So here I can say that B is extra. So this B is definitely extra. This B is extra. Okay. Is this clear? So this B is extra. So you can remove this B. You can remove this B. Now, after removing this B, now nothing is extra. Now, what is the second step for the minimization? Like for the minimal cover? To find the minimal cover, what is the second step? Now nothing is extra. You can remove that B. This B you can remove now. Okay, because that is extra. So you can remove that. Now you can find redundant FD. Is this redundant FD? Here what is C plus? Yes, this array clearly, this is clearly redundant, right? So you can remove this. C determine A, C determine A. So you can clearly remove this. Okay, among these two, any redundant FD do we have? No, there is no redundant FD. So finally your minimal cover will be what? Your minimal cover can be AB determine C and C determine A. This is your minimal cover. This is one possible minimal cover, right? Correct? This is one possible minimal cover. Okay, this is one possible minimal cover. So this is what the question is asking. This is what the question is asking. Actually the Ullman, this Ullman question, what this Ullman question is asking? This Ullman question is asking that in each case, just give one minimal cover. Just in each case, just give one minimal cover. Okay, this is what the question is asking. Nikhil, is this clear? Tell me. Nikhil, is this point clear? In each case, just give me one minimal cover. Like for example, is this minimal? Is this minimal? Look at this and tell me, is this minimal? You can check it out. This is minimal. You can check it out. Okay, this is minimal also. This is minimal cover also. And what about this? Is this minimal cover? What about this? This is not a minimal cover. What about this? Is this minimal cover? Is this irreducible? Is this irreducible? So this is not irreducible. Clearly you can remove that. You can remove this E. This E is extra. You can remove this E, right? This is extra. Clearly you can remove this E because that is extra. Okay. This is extra. Now, once you remove this E, then you can remove D determine A. So you can remove this completely. Right? Yes or no? Okay, because this is extra. This is extra. So you can remove this. And once you remove this, you can remove D determining A. Okay. So from here, what about this? Is this extra? Here, is there anything extra? Here, is there anything extra? So here, nothing is extra. So from here, you will get D determine A, AE determine D. This is minimal cover. Okay, like this you can do. Okay, so the remaining two questions I give you as a homework. This question and this question. So what you will do with this question? This question and this question. Write your answer in the comments. Okay? Comment your answer.